Hello, class. Welcome to the next segment in Lecture 19. And this segment, we're going to talk about the idea of a cold front, talk about some of the characteristics behind it, and just talk about cold fronts. So with that, let's go ahead and dive right into it. So I imagine all of you, if most of you, if not all of you, have seen some of these symbols before. So typically, a cold front is represented on a weather map as a cold, or as a cold blue line with triangles pointing in the direction the front is traveling. And this is typically what you'll see in a surface map. And generally, when you're looking at front symbols on upper air maps, the symbols along the line will actually be open. So here the symbols are closed and filled, whereas the symbols on an upper air front will in fact be kept open to sort of signify that this is not a surface front, this is a front that's occurring above the surface, say at 850 millibars, 700, 500 millibars, or some maybe even a level even higher than that in the atmosphere. And typically what you get with the cold front is you get a fast-moving frontal boundary that can move from north to south. If it's especially if it's an Arctic cold front, you'll get north to south motion. But if it's, say, a cold front originating from the Pacific or from a more typical cyclone, it's typically a cold front that moves from west to east or northwest to southeast, depending on what stage of the cyclone is at in the Norwegian cyclone model. So if it's in the developing stage, you're probably more likely to get a cold front that moves from northwest to southeast. Whereas in the maturing stage, you're much more likely to get a cold front that moves from west to east. And then as the occlusion takes place, technically you can get a cold front that moves from southwest to northeast in a very small area, but usually it still moves from west to east. Another interesting thing about cold fronts is they typically have a very steep slope. That is, the cold air within the cold front tends to have a very steep slope. It tends to, we'll take a look at a cross section and you'll see what exactly I mean by that. But as a consequence of that steep slope, cold fronts tend to produce really strong vertical motions in the atmosphere. And as a result of that, again, we'll talk about this in some greater detail, both in this lecture and some later lectures, but because of those strong upward motions, cold fronts are typically responsible for triggering some of the strongest and most severe thunderstorm activity that we see in the plains. And fronts that originate from the Arctic, so you can have a really large cold front that comes down from the Arctic regions, and those typically cause cold air outbreaks, and these are also usually associated with winter weather events. One of the biggest cold air outbreaks on record, I don't know if it's actually been broken, but I believe it was in 1899. In February 1899, there was a massive outbreak of Arctic air that produced low record temperatures that still are not broken still have not been broken to this day. I believe that was also the same outbreak where an observation station in Florida, of all places, recorded a sub-zero temperature in Fahrenheit, and I believe that's still the only time a sub-zero temperature has ever been recorded in Florida. I believe it was in Tallahassee or somewhere really close to that region of Florida. But in the extreme cases, these Arctic cold fronts can result in some pretty impressive cold air outbreaks. Cold fronts the vertical structure tends to vary quite a bit. You can have a really shallow cold front, or you can have a really deep cold front. And typically, by shallow cold front, I mean a cold front that doesn't extend more than 50 millibars above the surface. And a deep cold front would be something that extends up to, say, 925 or 850 millibars. But really shallow cold fronts can be responsible for prolonged rain events, or if the temperatures are favorable enough, these can also result in freezing rain events. There was one event of particular note that occurred in central Oklahoma and parts of northeast Oklahoma, where there was a lot of tropical shower and thunderstorm activity. It was very tropical nature, very heavy rain, and then a very shallow cold front came in and undercut those showers, and you ended up with a sub-freezing layer of air near ground level, and that was just ordinary tropical showers ended up turning into very torrential downpours of freezing rain. I think within about 15 or 30 minutes, there was 3/4 of an inch of freezing rain or something like that. It was ridiculous. And the reason why that occurred was because it was a really shallow cold front that came in, dropped the surface air below freezing, and all that rain suddenly became freezing rain. And boy, it did accumulate very rapidly. That was really something to see if you were in that event. That was back in 2018. But again, shallow cold fronts can result in not only prolonged rain, but if the conditions are right, they can also produce freezing rain events. And strong cold fronts, again, that goes back to strong upward motions. And again, we'll talk about this in greater detail when we go into our severe weather unit. But cold fronts, most oftenly, if you're going to get showers or thunderstorms, you're going to get lines of thunderstorms. But you can also get what's referred to as squalls, which are fast-moving regions of precipitation that are also accompanied with strong winds. And this can take the form of a snow squall or a squall line, which is usually referred to as a line of thunderstorms. But a snow squall is basically a squall line, but instead of rain, you're getting snow, and you've also got strong winds behind that as well. And weaker cold fronts typically favor more isolated convection, which is what you want to get if you're looking for a potential tornado outbreak. You want nice isolated thunderstorms which have a better chance of becoming supercells. And again, we'll talk about this in greater detail once we get to the severe weather unit, which will be fast approaching. And this is the cross-section that I was talking about. So again, I said that cold fronts typically have a very steep slope and they produce strong upward motions. This is what I mean by a steep slope. This interface between the warm air and the cold air, that interface is very steep. As you go up that interface, you're going up very rapidly. And this is typically what results in the strong upward motions, as this very steep layer of cold air displaces the warm air upward. It displaces it very rapidly and thus gives you very strong upward motions. In contrast with a warm front, where that displacement of warm air is much more gradual and much weaker, but that'll be a topic that we cover in the next segment when we talk about warm fronts. So with that, I will see you all in the next segment.